Saturday afternoon when we could all be out on the beach or walking through a forest or doing something else with our spare time. We're all sitting here dedicated to trying to work out ways that we can move forward and do something about climate change. I think that's really important that that level of dedication exists. So I'm, just to fill you in a little bit, I'm out at Forbes in central New South Wales. Forbes is a wheat, sheep sort of a district, cropping and grazing sort of a district. I work as an agronomist, so I look after farmers and help them grow their crops and pastures and livestock on a consultancy sort of basis, with a specific bent on looking at soil health and soil carbon. And we started a not-for-profit research institute officially about 3 years ago, but loosely about 6 years ago, when a group of farmers and soil scientists and myself got together and thought we need to find a way to help agriculture become better in climate terms, from carbon sequestration through to actual surviving climate change. Since then, we've had some really hard seasons to handle, and I'll get to that in my presentation. I put together a little bit of a PowerPoint presentation just to lead you through who we are, what we're about, what we're trying to achieve, and why we think it's important. So I'll whiz through that, and then I think we might have, it's sort of only about 15 minutes, and then at the other end, let's just chat about it, open to all the questions and ideas that you might have. One of the people that we have in our SoilCQuest group, really lucky to have, he was going to try to make this call, I'm not sure if he's on it or not, the guy called Frank Ollie, had quite a career in TV and movies and so on in the Northern Hemisphere. Accidentally fell in love with an Australian girl and got dragged back to Bogan Gate out here near Forbes, and became a farmer for a couple of years, and got a little bit itchy feet again and wanted to do some more TV sort of stuff. Decided to do a documentary, and he decided to do a documentary on SoilCQuest. So he did a documentary that went global. Last year it won all sorts of awards in all sorts of countries all around the world, about the idea of agriculture having a hand in a solution to climate change. And this little clip here is just a little 1 minute clip that Frank put together most recently, and I thought I'd be a good place to start, just to give you a bit of an overview and a feel for what SoilCQuest is all about. So,
sitting at home thinking about it, it's not good enough for me. I want to be a part of the solution.
Well, I truly believe that science is activism. Science is actually providing tools to fix a real world problem that needed solving yesterday.
So imagine a method that empowers farmers to take the carbon out of the air and put it into their soils on a gigaton, game-changing scale. A soil carbon capturing fungus, empowering farmers to become carbon capturing climate superheroes.
what I want to talk about today is what I've called the report from the front line. I want to really put agriculture and climate change together as a concept for everyone. As I say, I work as an agronomist, so it's a daily thing that's in front of my eyes that's happening. And there's lots to think about when we think about climate change in terms of agriculture and the impact of agriculture. So obviously the big elephant in the room is that there's too much carbon in our atmosphere, trapping heat and pushing the weather systems around the planet and amplifying extreme conditions. So the Ipcc report, the latest one, came out last November. 60 scientists from 40 different countries on the back of the 2014 Ipcc report, which I think was 69,000 authors on about 24,000 peer-reviewed papers. Very strong science. And they came up with some basic things that the people around the world, decision makers, need to think about. And this was one of the scary things, that we have 12 years to nearly halve our emissions. 12 years, you can count that in weeks. Limiting global warming would require rapid, far-reaching and unprecedented changes. Emissions would need to be balanced by removing carbon dioxide from the air. Long-lasting and irreversible changes such as loss of ecosystems. And we're already seeing the consequences of more extreme weather. So it's not something that is out in the future, it's actually happening now. So the important point out of those that came out of that November Ipcc report is this third one. Emissions would need to be balanced by removing carbon dioxide from the air. That's the bit that is exciting to me. So this is what I see through my agronomist eyes. This is the Forbes district, one of our local crop sprayers. Blackie took this photo in spring in 2016. And you can see all that water down there. There's unprecedented flooding for our district. A lot of my growers are down there, and a lot of their crops went underwater. They didn't get any yield at all because they got drowned. So extreme flooding in 2016. Then in 2018, 2 years later, if you look down here, down the bottom end of the middle of the picture, that's Lake Cow. That was actually, that's it there in the middle of that photo. So it's the exact same spot looking south from Forbes. The township of Forbes is just under the wing. And you can see that's the same time of year, 2 years later. And that is a picture of what spring looked like in 2018. Normally spring in Forbes is a picture, it's a sea of green and yellow. So yellow canola flowers as far as I can see, and green wheat up to your knees. This is a particularly fertile part of the district in Forbes. It's a well-known cropping area, been known to be a reliable cropping area. So it's a place where you can grow crops reliably, reliable rainfall and so on. That's 2018, what it looks like. There wasn't any crop to be had. It was just extreme drought conditions. Then the one in between, 2017, wasn't too bad a year. There was soil moisture from the previous floods, and there was some good crops growing. However, we had 60 frosts in a row. Forbes has an average of about 8 frosts in the rolling 100-year average. We had 60, 10 times the number of extreme frosts in that year. And that's what a head of wheat looks like when it's been frosted. So the grain doesn't develop. It gets frosted when it's just coming out and it's flowering, and the extreme frost will just stop that grain production part of the cycle with the plant. Same in canola. So there was lots and lots of yield washed off, really good crops that looked like they're going well, but we got smashed with frost. And this is this year, sorry, I've got that bit mixed up there. That's 2019. I took this photo a couple of days ago. So we're not yet reached spring. The weather reports for spring for our district is it's going to be dry. So we're not going to get any help in spring. So it's going to look worse than 2017. But this is our winter. And this crop here, usually this is canola, believe it or not. You can see the occasional canola plant. This is supposed to be getting towards up to your waist in canola this time of the year. It's sown in April. So, a few months later, you can imagine what a canola plant should look like. This is what all our canola paddocks look like at the moment. So basically there'll be no yield, no canola yield off that paddock. The soil's too dry to plant anything else. It's just sitting there idle. So that's my local district. What's happening around the planet? Has anyone seen this graph, this picture? People have been making t-shirt designs out of it and ties and things, which is kind of almost gruesome. You can see on the bottom x-axis, starts at 1905 and goes through to 2018. So the left-hand side's 1905 and the right-hand side's 2015. And they're all the temperature records for all the places around the world: Pacific, Asia and Middle East, Africa, Europe, and Americas. So over that time period, you can see where the temperature's been going from the light blue where it's been cool, as you scale up here, right through to where it's it's getting up to 1.5 degrees, 1 to 1.5 degrees increase in temperature since 1905. So that's all the global records aggregated into a pretty design. So yes, what I've been seeing is indeed a global phenomenon. It's happening everywhere. Extreme heat events, extreme cold events, extreme rain events, extreme weather. So it's a simple fact that when we put more carbon in the atmosphere, it traps more heat, which means more energy, and that increases the extreme weather events that we're seeing. I think Dr. John Church, quite a famous Australian climate scientist, actually worked it out in Hiroshima bomb equivalence, and it's equivalent to 4 Hiroshima bombs per second being exploded in our atmosphere worth of energy that is being trapped by the carbon dioxide that's been built up since pre-industrial times. So it's a massive amount of energy, that extra energy that's going into the troposphere. A lot of it gets absorbed into the ocean and the land, and then radiated back out and driving extreme weather events. So my point is, it's really hard for farmers to grow food under those conditions. It's extremely hard. And these last 3 or 4 years that I've experienced here and others have experienced around the globe is proof of that, you're not just reducing yield by 5 or 10% in some in the extremes that we've been seeing. We're just not producing any food. Like the paddocks that usually are producing 2 to 4 tonnes of grain per hectare year in, year out, in the last 4 years have produced none. So these extremes can have extreme implications on agricultural production. And it's really the elephant in the room. Imagine going down to the supermarket and seeing shelves like that. So modern civilization is founded on agriculture. We all eat 3 times a day, and we don't think too hard about where that food comes from. But it's got to come from agriculture. It's got to be grown. And farmers only need 2 things to fulfill that service. They need a healthy soil, and they need a stable climate. Without that stable climate, it becomes very hard for agriculture to produce the food that's required for our civilization. The world is only 3 meals away from chaos, is a famous quote by Lenin that many of you may be familiar with. So the question is it 1.5 degrees is our target? Is it 2 degrees Celsius our target? Where do we draw the line? We've seen a 1 degree increase in global temperatures on average, and we're already seeing this kind of extreme conditions that are making it really hard for farmers to grow food. So what's 1.5 look like? What's 2 degrees look like? Just untenable, I would say, from an agricultural point of view. So are we sleepwalking into an irreversible climate crisis? So pretty sobering, and obviously we need to keep optimistic about what we can do and to turn this beast around. So what are some of the things we can do from a really practical standpoint? And that's where SoilCQuest has come about, through farmers thinking about this, about how soil and agriculture may be able to play its role. And if you look at the picture on the screen there at the moment, that's basically the soil map of where the carbon intensity is in our soils around the world. And that carbon sink, it represents the single largest terrestrial carbon sink on the planet. It's only vested by the ocean as far as a carbon sink. The world's soils hold twice as much carbon as all the vegetation put together and all the carbon in the atmosphere. So it's a huge carbon sink. That's it in practical terms. The heat intensity map here of all the places, the food baskets around the world where we grow food. That's the annual cropping zones of the world where we grow all our cereals and pulses and all our food crops. So we farm, as in terms of growing crops, an area about the size of South America, if you put all that together, and we graze an area about the size of Africa as humans. So it's a very big footprint that we have on the planet that is actually managed by farmers. So that makes farmers potentially the world's largest and most important climate army on the planet, because they actually manage the biggest carbon sink on the planet. And if you do the numbers on how much carbon we actually need to pull out of the atmosphere in order to balance the books, soil's big enough, well and truly big enough, to accommodate that amount of carbon. So the conduit between the dynamic that there's too much carbon in the atmosphere and not enough in the soil is the farmer himself, herself. The process that we want to talk them into doing is to work out how we take that carbon from the air and sequester it into the soil. And to do that, we need to have really practical and really economically sensible ideas that allow a farmer in their normal economic running of their business, because farming is a business, to be able to do that job. So far to date, we've paid farmers as a society to decarbonise our agricultural landscapes. So we've paid them to remove trees from the landscape so that we can farm our crops. We've paid them to remove carbon from the soil by merit of how we're required to grow these crops. Everything that we do in agriculture is about taking carbon out of the landscape rather than putting it in. So the only answer is to work out how do we recarbonise that landscape, that agricultural landscape? How do we make it financially feasible for farmers to get paid for putting more carbon in than they're taking out? So that's where SoilCQuest was born, out of that concept. And we've been working on a wave that came out of Sydney Uni that involves a particular type of fungus, what we call the soil carbon inoculum. That's it on a petri dish in one of our labs. Fundamentally, it's a fungus, what they call a dark septate endophyte, melanised endophytic fungus, that makes a particular black substance called melanin. So melanin is the same compound that we have in our freckles and that exists in human skin, and we see it all through nature. Anything that's dark coloured in nature has to do with melanin. So melanin is a very interesting compound. It's very recalcitrant, so it doesn't break down easily, and it can be manufactured by these fungi in large quantities. That's what it looks like under magnification. So you can see that's spider web sort of material, that's the hyphae of the fungi, and you can see how black that material is. It's just a really short animation of how the concept works. So we inoculate the plant with this fungus. It lives in harmony with the plant inside the roots, and it extends its hyphae out from the roots. It uses some of the carbon flow that the plant is taking out of the air as to produce sugars in the photosynthesis, and it distributes that carbon out into the soil safely in soil microaggregates. Just do that again quickly because it goes through pretty fast. So you can see the carbon coming out of the plant. He's made that through sunlight and carbon dioxide, producing sugars. The fungus metabolises that sugar, turns it into melanin, and then distributes that melanin out into the soil, into these little areas we call microaggregates. So soil is made up of macroaggregates and microaggregates. In simple terms, microaggregates are just little clumps of soil about 200 microns in diameter. So these tiny little clumps of soil that different soil biology are clumped together. And on the inside of those microaggregates, it's an anaerobic zone. There's no oxygen on the inside of these little tiny clumps of soil. And these fungi go in looking for food resources inside these microaggregates, and they deposit the melanin inside the microaggregate. And because there's no oxygen there, there's no oxidation, and that's the enemy of carbon in the soil is oxidation, because that reaction turns it back into carbon dioxide. So we don't want that to happen. So we're trying to store it in places in the soil that don't have much oxygen. So a healthy soil has lots of oxygen in it, apart from inside these microaggregates. So that's the good place to put it, inside the microaggregates. or down deeper in the profile. So as you go deeper down the soil, there's less oxygen, and melanin, the material that these fungi are making, can actually percolate down through the profile deeper and deeper down in the profile away from oxygen. So we're not only making a lot of carbon, we're making a lot of stable carbon by using these fungi. So in essence, it's a carbon capture technology. So I'm not sure whether your boxes are covering the far right-hand side of this slide or not. It is on my my screen, but on the far right, you'll see MEF222. That's one of our isolates with canola growing in a tube, and on the left-hand side is the control without the fungus. So you can see there what's happening, that the fungus is growing using the carbohydrate flow of the plant and depositing that carbon in and around the root system. Every moment that that plant is making sugars, the fungus is turning some of those sugars into melanin. And that's the stuff that we want to increase. So this particular isolate we call 222. In the work at Sydney University, they gave 17% increase in soil organic carbon in 14 weeks. That's unprecedented rate of carbon sequestration for soil. That's really fast and really significant. So that's what initially excited us about the research, and what's driven us on of taking this forward. So we envisage that it'll just be a simple seed treatment, so something farmers can easily and conveniently just coat the seeds with the spores of the fungus, and then go out and sow that seed in the soil and grow their crop. The fungus starts growing in amongst the roots and distributing carbon in and around the root zone of that plant. So we just do a little bit of maths in our head. Imagine a paddock, a hectare of wheat. So it's a bit bigger than a football field, a hectare, and you've got a wheat crop growing in that 1 hectare. And you've inoculated it with the fungus, and the fungus is growing with the roots. So it starts off with this tiny little root system from the seedling and gets bigger and bigger and bigger until it's a root ball, about the size of a soccer ball, for example. And in a halo around that soccer ball size root system, the fungi grow out into the soil and depositing their melanin into microaggregates and into the soil. That one plant, all it has to do is, and that fungus, all it has to do is to produce 3 grams of melanin over about an 8-month period of that plant growing, to do a really big job. So 3 grams is about half a teaspoonful of melanin in an area of about probably 3 or 4 litres of soil. And then the calculation is that roughly there's about 1 million wheat plants per hectare when we sow our wheat crops, so about 1 million seeds per hectare. So you multiply that 3 grams per plant by 1 million, you have 3 million kilos, 3 million grams, which is 3,000 kilos, which is 3 tonnes. So 3 tonnes of melanin production per hectare. And then everyone talks in carbon dioxide equivalents. So you multiply to turn soil organic carbon or melanin into carbon dioxide equivalents. You multiply by a factor of 3.67. That's the conversion factor. So who's good at maths? What's 3 times 3.67? Anyone got a quick answer? Who's a good mathematician? Someone might have a calculator, but it equals about 11 carbon dioxide equivalents, 11 tonnes of CO2 equivalent per hectare per season. And then it's a simple matter of multiplying that by however many hectares that we think that we may be able to get farmers to adopt that on. And given that carbon is very good for the soil and increases water holding capacity, nutrient cycling, disease suppression, water infiltration, all the very things that we want our soil to be, carbon has a major influence on. So it's going to be something farmers will desire to use in their paddocks. There's going to be an agronomic outcome for them to use that. in their systems. So we can multiply it by all sorts of numbers, I guess, and work out how many tonnes it's equivalent to. But if we go back to that map of the potential of the world's soils where people grow annual crops, there's about 550 million hectares of arable land that's down to crops each year. Multiply that 11 tonnes by that, and you come up with 6 gigatons per year, or 60 gigatons over a 10-year period. If you convert that into parts per million of carbon dioxide in the air, it's equivalent to about 80 parts per million. So potentially the world's soils have the capacity to pull down the equivalent of 80 parts per million in 10 years, if we were to employ every farmer that has the capacity to use the technology. So that's probably a bit of fantasy, thinking that you can employ every farmer to do the job. But if you were to, under duress, when people are starting to wake up how serious climate change is and what an existential threat that it really is, perhaps it's not such a stretch. So some of the things that we do as an organisation, we go out bush and we look for more of these endophytes. And we're looking for, we go out to really hot and extreme places. So this is right out western New South Wales last summer. Actually, this is the summer before last, this picture. And we look for the connection with these fungi that make melanin. They also help the plant to withstand water stress. The actual compound itself, melanin, triggers an expression in the plant to be better at handling water. So they close the stomata up a bit more, and they're just more efficient with water relations because of that compound melanin. And it's evolved in arid conditions very strongly, because you can imagine a plant that sets down carbon around its root system that holds more water, and the compound itself actually triggers the plant into a water stress relief condition, is going to survive better than the plant that hasn't got that fungus doing that job for it. So they both get to reproduce. The fungus gets to set some spores, and the plant gets to set some seed and live on another generation. You do that over thousands of successive years. Through the evolutionary process, you get a really fine-tuned fungus-plant relationship, and they're the ones we're really interested in. So this particular plant here, you can see the meat thermometer that we've used here. So we've jammed it into the ground 10 centimetres into the actual heart of the root system of this plant. You can see a few little green shoots coming up on that plant, and that's why we did this. And you can see the temperature at 10 centimetres, it's 55 degrees Celsius. At 10 centimetres down in the heart of that root system of that plant, it was wickedly dry out there. There wasn't an ounce of moisture in the soil. It was just bone dry. And yet here's a plant still putting up green shoots, going, oh, I actually don't mind it here. It's pretty nice. And, they're the sort of plants we're looking for. So we take plants like that and we isolate fungi off them. So I took my boys out with me for that bioprospecting adventure, and that's about the happiest they looked that day. It was exceedingly hot, 45, 46 degree day, and I took them back into the Cobar swimming pool that afternoon, and there was just about steam came off all of us. It was exceedingly hot. So we bag up the plants and we GPS point them so we know where they are, where they've come from, and we then take them to the lab. It's Jeremy, our microbiologist. So he isolates them out of the root systems, grows them onto agar, incubates them up, and then we characterise them under the microscope, see what they are, and see whether they're going to be useful to us. Then the ones that we think that are going to be most useful to us, we have to put into further trialling. So this is a glasshouse in orange. That's Dr. Chris Anderson. He's a very good microbiologist and soil scientist. And we grow them out in glasshouse and see what they do to the plant. We do core samples around at the end of the trial. We cut the plant off at the top, and then we do 3 cores around the root system of that plant and send those cores off to the lab to measure it for soil organic carbon. So in that particular one was Lab, which is a summer legume, and we do, I think there was 20 replicates of about 3 different treatments, including the controls. That particular one did a 7% increase in soil organic carbon in about 90 days, which again is astronomical soil carbon sequestration rates. When we've done that, we get a farmer and we mix it on his seed, and we take that out into the paddock and we do some paddock trials to see how it reacts with normal conditions, under normal paddock conditions, to see if it's actually growing carbon in the paddock. So that's the simplified process of basically what we do from the field, of finding the ones who are interested in, screening them down, running through the laboratory, running through glasshouse, then out into the paddock to see what they do out in the paddock. And we have a beer at the end of all that, hopefully. So we've only been playing with this for about 3 years intensively, and screening like mad and finding new exciting isolates and getting lots and lots of work done in the lab. But this was some work that was done by Jeremy, the microbiologist that you saw the picture of there previously. Jeremy's also got a property up near Wauchope, and about 10 years ago he went to a presentation by a microbiologist by the name of Elaine Ingham from America, and she had a throwaway line that carbon in the soil is built up by fungi that have black hyphae. And it was literally just a one-liner, but he wrote it down in his notebook and took it home, was reading over his notes and thought, that's pretty exciting. I wonder whether that's true. So he went out as a bit of a microbiologist, as I say, and he's isolated black fungi. Didn't really know what he was isolating. He just went out and found black fungi around his farm, fermented them up and applied them to one paddock and left the other paddock as a control. So it's just one side versus the other. It's not a replicated trial. It's literally just a demonstration of what might be possible. But these pictures here, you can see the top one is the soil after 10 years and about 15 applications of these fungi. And the bottom one is the native soil, what it looks like normally. And you can see obviously a distinct colour change there. And the paddock itself, you can see, is greener and a lot more productive in terms of extreme carbon sequestration. That's what he did. So there's some of the isolates that he used under the microscope. We're still trying to work out what they actually are, but they made melanin, melanised fungi. So on the back of that, we went out and we did a very intensive soil coring project. So we did multiple cores around either side of that fence line, the treated versus the untreated, to try to get some statistics and some science around what might have happened there. We took numerous samples and we divided them up into increments down to a metre, so they're metre long cores, and divided up and wrapped up in plastic so they can go off to the lab, and we can test the carbon all the way down the profile and find out where the carbon's being stored and how much carbon is actually being stored. And is there other things happening in soil? What's the carbon actually doing to the soil? Is it measurably improving the agronomics of that soil? So visually, there was some really obvious stuff. So with the carbon fungi, you can see it's darker and wetter versus without the carbon fungi. The full metre core, so we can see it's actually carbon being sequestered all the way down to a metre and beyond, versus the one on the bottom, which is the native soil, untreated. We isolated down about 800 down the profile, so not quite a full metre. We re-isolated some roots, and we were able to re-isolate melanised fungi from those roots. So they're existing 800 millimetres down, 80 centimetres down the soil profile. The fungi were happily living. And then we did some numbers on some stats. So the soil organic carbon from 0 to 15 centimetres right down to the full metre. The blue line is the treated, the red line is the untreated. And you can see all the way down the profile, carbon has increased over the control. Then we looked at total nitrogen and total phosphorus. So farmers are really interested in knowing, does this impact on their nitrogen and does this impact on their phosphorus? Again, the blue is the treated and the red's the untreated. And again, all the way down the profile, we've increased nitrogen. And for phosphorus, we improved the phosphorus availability, so a key nutrient for crop growth, down to the 300 mark. And down below that 300 mark, we didn't increase it at all, which was, we still really don't know why. But we've got quite a dramatic increase in phosphorus availability in the top 15 centimetres, which is obviously the root zone for the plant. So there's some significant benefits for the farmer there in productivity, and you saw by the greenness of the paddock in that first photo that making a difference to pasture growth. Moisture, so again...
Excuse me, Guy.
Yep.
Hello, Guy. It's Tom here. Sorry, I stuffed up at the beginning there, no end. I should have pointed out we have limited time today, and so we're running a little late. Just thought perhaps you could wrap up there. This is a wonderful story. I hate to cut you short, but this is, yeah, there's a lot of people expecting it to be a bit shorter, that's all. Thanks,
okay,
guys.
so probably got about 3 more slides, Tom.
Okay, good, thanks.
Rightio. So moisture and pH increased all the way down the soil. So they're really important parameters for farmers to consider. It makes their soil more healthy is basically the simple point. But when we added up all the carbon down from a metre, we pulled down 150 tonnes of carbon dioxide equivalent per hectare. So that's a very big number. So carbon capture and storage into the world soils where we actually need the carbon. It's good for the climate, it's good for the farmer. There's a few things we need to do as we're going forward. But in simple terms, it's worth money to the farmers to adopt this sort of technology. So that's our vision, is to fix the climate by fixing the soil. Thanks very much.
Thanks, Guy. That's fantastic. What a wonderful story you've got there. We really appreciate you putting this effort into giving us your talk. We might have a few questions before we go. We're a bit over time, but has anybody got any pressing question they'd like to unmute themselves and present to Guy, please?
I have one.
Yeah.
That's a pretty big difference between, so what you were originally saying was 11 tonnes CO2 equivalent per hectare to 150 tonnes equivalent CO2 per hectare. Is that, I mean, do you have any sense of the reason for that?
So the 150 tonnes is over a 10-year period. So that's, so you divide that by 10, you've got 15 tonnes per hectare.
Gotcha.
So we're targeting something around that 10 or 11 tonnes to be conservative. But it is exciting that, you know, we can demonstrate over a 10-year period we've done 15 tonnes per hectare, and that's in a really light, horrible soil, very acid, not very high in nutrients. The biomass wouldn't have been fantastic over that 10 years. So we feel 11 tonnes is really super conservative, but that's the best place to start. But potentially, you know, we could be quite easily doing double that.
And is there a limit? Is there a limit to what the soil can take, like, or what's healthy, or I don't know? Yeah,
that's a common question. I don't think that's our problem, but it'll take, you know, hundreds of years to get to, say, 50%. You know, some of our peat soils around the world might be up to around 50%, which is super loaded with carbon, but they're some of our most fertile soils. So, you know, there's lots and lots of space in the soils to fill up with carbon. That's not the limitation.
Sure, thanks.
Yeah, good question though, Nell.
Thanks, Nell. Any other questions? One last question, perhaps.
There's one with a hand up here. I don't know the name there.
Yeah, so what plans are there for some large-scale trials of this kind of fungus technology?
Yep, so we're right in the middle of doing negotiations with some very large funders for this project. So we've been beating the drum trying to get money together by crowdfunding and all sorts of ways, pleading and borrowing to get this research done. It culminated about 2 or 3 months ago that Mick Wettenhall, who's one of the other directors, he's a farmer up at Trangie, happened to have a friend that worked for the BBC, and she was really curious about the story and wanted to know more, and thought, oh, we could do a story on this. And time went by, and finally she got around to it. And she said, Mick, do you mind just doing a Zoom to BBC for some breakfast TV? So, yeah, as I say, 2 or 3 months ago, he did that, and he had 4 minutes of breakfast TV that went out to about 85 million people globally. And one of those people was a very major philanthropist that took an interest in the story, and within 15 minutes was actually in contact with Mick at Trangie. And the next morning we had a Zoom meeting with them, and we've been in negotiations since, working out how we're going to work together and do this. So it's not a done deal yet, but I'm hopeful that we've attracted enough attention to get the interest of these sorts of people that can support the funding for the project, because it's a tricky sort of stage. There's lots of scientific grunt work still left to do. It's not a done deal like we can just brew it up and give it away to all the farmers and away we go. We've got lots and lots of science to do around it to really validate it. We've got an interesting idea, and we've got proof of concept that's possible to do it, but that's not the same as having something ready to deploy globally. Like the due diligence around deploying a living organism around the planet is huge, and we need to make sure that we're not deploying a cane toad. So there's lots of science that's got to go into it, and it's quite expensive science. So that's always been the limitation of where we get money. We're hoping that we're in the process of getting some money to do that early stage research.
Guy, are you still looking for government support for that, or what's the status of that?
Yep, yeah, no, we certainly are. We're lucky enough we won one of the Smart Farms grants, the Landcare Smart Farms grant. So we have got a small amount of money to do some initial trials through 4 Landcare districts through the central west here in New South Wales. So that hopefully will give the organisation enough exposure to go for other grants and to get some government support. Having said that, I've had 3 meetings with our Deputy Prime Minister, Michael McCormack, and because he's our local member. So I've been able to orchestrate some meetings with him. The last meeting was about 2 weeks before the elections, and I asked him what was in the budget for soil and soil carbon. He said, zero. It's all going to be bridges, roads and dams. So not much support from our Deputy Prime Minister, unfortunately. I think the whole climate argument is a bit beyond him. But I'd like to think that was going to change, and I'd like to think that people like you would go in there and advocate for more work to be done in this area. And I'm certainly keen to be part of that process if there's any opportunities. But yeah, my responses so far haven't been very, a lot of nodding and a lot of kind of smiling, but not much action from the sector.
Thanks.
Well, we need to get on board. We really appreciate you giving us your time this afternoon, Guy. And what a fantastic story. We need to get right behind this. Amazing stuff that you're doing there. Thank you very much. If everybody could show their appreciation for this wonderful talk this afternoon.
Someone's got a t-shirt. Who's got the t-shirt?
It's me. I bought it a little while ago, not really fully understanding the whole process. So it's really nice now. I'll be able to wear it and understand a bit more about it. So thank you very much.
Thanks so much for your support. That's really heartening. Good on you. Thank you very much.
No worries.
All right. I'll leave you there, I think. Is that the process? You guys got other things to do?
Guy, before you go, I just want to use my chairman's privilege to ask you one further question, and that is, how would an effective, efficient carbon price make it easier for you in your work, and later on make it easier for farmers? or would it make it harder? It's important for us to have a sense of that.
Yeah, so one of the pull-through mechanisms that we're in conversations with some really some of the bigger carbon trading organisations around the world, like Gold Standard and Vera, South Pole, those kind of organisations that work in carbon trading. They're obviously very interested if we can come up with a way to produce more carbon credits into the voluntary and non-voluntary market. They're saying that there's a deficit of supply, there's a huge demand. So, they're interested in how do we generate these carbon credits. There's also precedent this year, only a few months ago, the very first carbon credit was traded under the ERS, under the Paris Agreement in Australia, down in Victoria. So Australian first, world first, really exciting. One of our team members was responsible for the carbon testing on all that. So there is a precedent that we can trade carbon, but we really would like the ability for farmers to get rewarded from society at large for doing a social service, for pulling down carbon out of there and putting it into the soil. They could get paid for that process. That'd be a really strong pull through for the technology and allow deployment to happen faster and further. So yeah, it's a really important point. Yeah, thanks, Rod. Yeah. What's your thoughts on it?
Well, we're very keen to create a carbon price in Australia and globally, and that that's part of our proposal. And we believe that what we're doing will make carbon more and more valuable and make it easier for farmers to get paid for their service. So I think it's really important.
Absolutely brilliant. Anything I can do to help that process, Rob, just call me anytime, day or night.
Well, Guy, I'm just about to pull up an advertisement for our, not an advertisement, a flyer for our next conference. So if you could stay online and see that.
Okay.
You might be able to come to our conference, which should be happening in the middle of September. We're still waiting to hear from the government as to what their sitting dates are, because obviously we want to meet during sitting dates. But that's the draft flyer. It'll be sent out. The final flyer will be sent out shortly. But just to give you a picture of it.
Great. Yep.
And
it's in Canberra. Great. All right.
And there's the second page of it.
How cool. I love the graphs on the front page. That's awesome.
Isn't it good? Yeah.
Who thought of that? That's a good idea. Yeah.
That was Tom who asked your second question. We'll give him the credit for that. It was excellent.
Yeah, that's genius. Good stuff. Yeah. All right. Yeah. No, I'd love to come to that just to have a look, and send me an invite. I'll come along. Definitely.
We'll send you an invitation.
Rightio.
And my the dates are confirmed now.
Oh, the dates are confirmed. Great. Excellent. So it's definitely that middle weekend in September. So we look forward to seeing you there, Guy.
Good on you. Thanks very much, everyone, and talk soon. Thanks for your time.